Hello, everybody. My name is Cameron Joyce, and I'm a part of Group 4. This is for ME 2191, and I'll be going over a Type 4 question. In this case, it is 2.132, the question you see on screen. Um, this particular question involves a polystyrene rod consisting of two cylindrical portions AB and BC, which are restrained at both ends and support two 6-kip loads as shown. Knowing that the E constant is equal to 0.45 times 10 to the 6 psi, determine A, the reactions at A and C, and B, the normal stress in each portion of the rod. So right off the bat, we can see that the diameter for the higher portion of the rod, portion AB, is 1.25 inches, and that the diameter of the rod, portion BC, is only 2 inches, while the length for AB is 25 inches, and then the length for BC is 15 inches. So we know that this particular question is a type 4 because the two rod portions are confined in between two fixed points, which you can see on the top here and on the bottom, which is identical to type 4 according to the notes. Knowing this, we can proceed to, excuse me 1 second, proceed to my notes here to actually see how we solve this particular question. So right off the bat, you can see that I've redrawn the question diagram. We have the rod ABC with the diameter 1.25 inches for AB and the diameter 2 inches for BC, and their length accordingly 25 inches and 15 inches, and the two applied forces at 6 kips. We have our known E constant of 0.45 times 10 to the 6 psi, and we're looking for the reactions at A and C and the normal stresses in each portion of the rod. Now, in the free body diagram, we have the reaction force of A pointing upwards. We have the two 6-kip forces being applied downwards on the portion BC. And we have the reaction force C also pointing upwards, similar to the example in the type 4 in the notes. Now, assuming that the positive y direction, or that the positive y direction is upwards, the summation of the force of the y direction should equal 0. Now, this is also similar to the deformation because since this problem is fixed in between 2 points, there won't be any shift. And because we're orientated in the vertical direction or positive y-axis direction, it'll be equaling 0. So we can write that the reaction force of A plus the reaction force at C minus the two 6-kip loads equals 0, which can be rewritten as the reaction force of A plus the reaction force of C equals 12 kips. We can also break down the diagram or free body diagram even more into these three portions similar to the notes, such that you have the reaction force of A pointing upwards, and there's a resultant reaction force A pointing downwards, and we'll have the force of AB pointing upwards. And we're just going to look at this portion real quick, just so that we can understand the force of AB equals reaction force of A. Since the force of AB and the reaction force of A are pointing towards one another, and in this entire example will end up being have a deformation of 0. We know that these two forces will have to cancel each other out. Therefore, they'll have to be equal. And since this reaction force here, this RA and this force of AB cancel out, the reaction force of A is in the positive direction, so that we know that the force of AB is directly equal to the force or the reaction force A. Continuing downwards, we see that we have the two applied 6-kip loads, which we can find in this equilibrium equation right here on the top, our reaction force A plus the reaction force C minus 6 kips. Minus 6 kips equals 0. And proceed down to right here where the reaction force of C points upwards, but the force of BC is pointing downwards, and the reaction force, or the resulting reaction force C, is pointing upwards, And since they're pointing away from one another, but we know that they have to be directly equal to each other in the instance to where there's going to be zero deformation, we know that they're going to be equal to one another. But because they're pointing away from one another, so in this case, force of BC and force of RC will cancel each other out, we know that it'll end up being a negative reaction force C. So force of BC is equal to the negative reaction force C. Continuing on, from the notes, we also received the equation that deformation is equal to the force of AB times the length of AB over the cross-section area. In this case, it'll be pi over 4 times the diameter squared of AB times the E constant plus the force of BC times the length of BC over pi over 4 times D squared, or the diameter squared of portion BC times the E constant. Again, because this type 4 problem is fixed in between 2 points, we know that deformation will equal 0. And rewriting the equation or substituting in our previous conditions that the force AB is equal to the reaction force A and that the force of BC is equal to the negative reaction force of C, we can write that reaction force of A times the length of AB over pi over 4 times the diameter squared of AB times the E constant minus, again, because of the force of BC equals negative RC. Right here, we can substitute that in, minus the reaction force of C times the length of BC over pi over 4 times the diameter of BC squared times the E constant. If we add this RC portion, the reaction force of C portion, over to the left side, and then multiply by the pi over 4 times the diameter, of portion BC squared times the E constant to the right side of the equation, and then divide by the length of BC, we're left with the reaction force of C is equal to the reaction force of A times the length of AB divided by pi over 4 times the diameter of AB squared times the E constant times pi over 4 times the diameter of portion BC squared times the E constant over the length of BC, which can be simplified down to the reaction force of C equals the reaction force of A times the length of AB, which is 25 inches, over the diameter of AB, which is 1.25 inches squared, times the diameter of portion BC squared, 2 inches squared, divided by the length of BC, which is in this case 15 inches. If we simplify that, we're left with the reaction force of C is equal to 4.2667 times the reaction force of A. Now, if we put this resulting equation back into our previous equilibrium equation of reaction force of A plus the reaction force of C equals 12 kips, right here, we're left with the reaction force of A plus 4.2667 times reaction force of A is equal to 12 kips, which means that the reaction force of A is equal to 2.278 kips. Similarly, if we insert this resulting answer for resulting force A into that same equilibrium equation, we get 2.278 kips plus the reaction force of C is equal to 12 kips, which means that R of C, or reaction force of C, is equal to 9.722 kips. And that solves our first portion, or gives us the reactions for A and C. And if we proceed to part B, we are going to find the normal stress in each portion, in this case, portion AB and BC. So sigma, or normal stress, of portion AB is equal to the force of AB over the area of AB, which is equal to the reaction force of A, which was from our previously stated force of AB is equal to the force of RA, or the reaction force of A, divided by the area, pi over 4, times the diameter, squared, 1.25 squared, which equals 2.278 kips over 1.227 inches squared, which simplifies to the normal stress. The normal stress of portion AB is equal to 1.857 KSI. Now, for the normal stress in portion BC is equal to the force of BC over the area of BC, which is equal to negative RC, or reaction force of C, because we previously stated that the force of BC is equal to the negative reaction force of C over the area of portion BC, which is pi over 4 times the diameter squared, 2 inches squared, is equal to negative 9.722 kips divided by 1.27, divided by 3.1416 inches squared, which simplifies to the normal stress in portion BC is equal to negative 3.095 KSI. That concludes my work for question 2.132, and I hope that this helped you to better understand the question. Thank you.